Section is titrations. The first part is going to be definitions, and then we'll continue on from there. So, titrations incorporate everything. We start with our weak or acid or base, and then we start adding strong base or acid. So, if you're titrating a weak acid, you'll add a strong base. If you're titrating a weak base, you start with the strong acid. So, titrations involve weak systems, they involve buffers until you get to the equivalence point. More about that in just a second. And then they'll add a salt problem, and then they're strong. So, there are four parts to them. We'll get to those in the next part, but in this part, we're going to work on definitions. And again, as you read through the book, go ahead and read through the life and chemistry and life, etc. The little lanyards. They're not going to appear on the test as bonus points, I don't think, because of the way this is working. But they're interesting to look at. So, first thing we're going to do is we're going to talk about titrations. Okay, well, definition. A titration is a method of determining a concentration. And it can be of a solution, a solid, etc., by addition of another solution until you change color. Until, you produce a color change. Now, the color change is used with an indicator, etc. So, as we talk about titrations, you've done titrations, you did several in 1212. You've done the acid, weak acid, strong acid, diprotic to titrate. You've already done those. So, that's basically what you did. Most of the time when you do a titration, you use a stoichiometric amount, which is what you did in 1211. And we'll look at that as we go. The analyte is whatever is whatever concentration is being determined. So most of the time, it's whatever's in the Erlenmeyer flask that you added. If you start with a solid, you usually add water into the flask and you get it dissolved. Okay, the titrant is whatever is in the burette. Okay. Now, most of the time, the analyte is what you're adding to, and the titrant is what's in the burette. Occasionally, the known can be in the solution that you're titrating, and the unknown is in the burette. It can vary. As long as you know one of them, you can determine the other one. And the indicator is the species which changes color. At the endpoint, to determine the endpoint. Now, the endpoint is when the reaction has been reached. Okay, so as I said, with titrations, you've done these. It's relatively simple. The question is what's the endpoint? That is where there is a physical change. That means the reaction has taken place. And this is usually with an indicator. Now, occasionally you can use either the analyte or the titrant as having the color change. When we did the kinetics lab, if you'll remember, we didn't worry about amounts, but you took the permanganate, which was purple, and the oxalate, which was colorless, and it went to a light yellow and eventually a clear solution. Okay, that's one where you don't need to add an indicator because the indicator is built in as one of the two species you're using. Okay. In acid-base reactions, you use indicators because most of them do not have a color. Now, an endpoint is where you see the physical change. The equivalence point is the stoichiometric endpoint. Reaction has been reached. What does that mean? That really means that your moles of titrant equals your moles of analyte. Or moles acid equals moles of base. Now remember, you get the moles when you take the volume times the molarity, because that is liters times moles over liters to produce moles. Okay, now as we work problems later, we may do this in millimoles. And I'm going to go ahead and put this here, and then I'll do it again, because that means you use the volume times the molarity still, but now you're going to use milliliters times millimoles over milliliters, which gives you millimoles. Okay, and this is often used when we do titrations because we're using small numbers, and it's easier to say that you have 12 millimoles than it is to say 0.012 moles. Now, again, it's personal preference. I'm going to do things mostly in millimoles, but if it makes you happy to work them in moles, it is perfectly fine. You will get the same answer. Okay? So when we did the titration curves that we did previously, you looked at, you graphed them and you saw what you got. So what you're seeing here is a graph. Notice that this is the volume and this is the pH up here. Okay, and when you're titrating a weak acid, you're going to start or in this case a strong, you're going to go up and then you have this huge inflection. If you'll notice, you're going to go a very large pH range at one volume. Okay, so your equivalence point is halfway up the curve. Now, the trick is, and we'll talk about this in a minute, is making sure your equivalence point and your endpoint, which is indicated by the color, are the same. And this is easier to achieve when you have a huge inflection. Okay, so that was a strong acid and a weak base. This is a strong base with a strong acid. If you look at it, it's pretty much inverted. We start high and we go low. We're still doing pH and milliliters added. We still have a very large inflection point. Okay, it's just starting at a high pH and going down. When you titrate with a variety of acids, there's your strong, here's your weak, and you're getting weaker as you go up these acids. So notice that as you get weaker, your inflection points change. So as you, let me do this in reverse, decrease the strength, you decrease the pH inflection. So what that means really is that you don't get as big of a range. So it becomes more critical that your endpoint equals your equivalence point. Now the other thing I want you to look at is what happens in this region. Notice that with strong acids, it's pretty much a straight line. But as you get weaker, you go up and then you kind of have this region here that levels off. This is going to be your buffer zone. And we'll look at this in more detail when we do more detailed graphs. But when you look at the graph, it tells you a lot. You can tell whether it's a weak acid, weak base, strong acid, strong base. If it's a weak, how weak it is based upon the inflection, etc. If you have a diprotic acid, and we looked at those previously, you're going to have 2 pKa. So notice when we did this before, and you should still have the data on your computer, you get not 1 equivalence point, but 2. And notice that you have 2 different inflections in leveling them off. And again, you would have 2 buffer zones. All right, now the trick part is the indicator. You need an indicator that is based upon your endpoint. Okay, so remember a couple things. One, only strong acids plus strong bases have a pH equal to 7. Those are the only ones. Okay, most are if greater than or less than 7. So you have to pick an indicator that hits your equivalence point, pH. And this is critical. And I'll walk you through that real quick. Now, the indicators are acid-base indicators. When we did the one that we did in the aqueous reaction and we looked at it, we ended up with the color change, and that was the pH is equal to the pKa. So that actually gave you the K value for them. Most of them are weak acids, so they're typically a Ka. So it works as a simple Ka with the acid being one color and the base being another color. When we look at this, figure 16.8, this, if you look at each point, this is where it's equal, and then it changes color. Now, some are more extreme, like they go yellow to violet. Phenolphthalein goes colorless, so this should actually be clear, more like that, to pink. So that one's an extreme. And some of them are much harder, like methyl red is between red and yellow. And if you end up with color blindness, you may not be able to see because the conversion is right there at orange, which is really hard to see. But different color indicators have different ranges. So notice that if your equivalence point is about 0, you use methyl red. Phenolphthalein will not work for you at all. So you pick them based upon that. This is another figure that has more with the color changes in it. And if you'll notice, several of these were the ones we used in the aqueous reaction because they had much more. Again, here's your phenolphthalein. Phthalene does pretty much the same thing except it's a higher pH. So you would choose your indicator based upon what your pH is. If your endpoint is right here, your equivalence point is right here, you need your endpoint to match. So you would choose one of these two. Okay? Something lower wouldn't work for you. Okay? Now, because I can't give you the entire list, I've picked a few out and I give you a range. So if I told you that the equivalence point is going to be about 4, which indicator would you use? So if the pH for the equivalence point is about 4, then you would want to use methyl orange. If it's very strong and you have a huge range, then you can get away with things like phenolphthalein, etc. So the bottom line is you'll be giving an indicator list when you're asked to titrate. Okay, so this is a visual of this. If your equivalence point is very large, in terms of the inflection is very large, then you can get away with anything on it. But if your equivalence point is not, or your indicator is outside your inflection point, then this one would be bad to use this one. This one would be a good indicator to use, and is strictly a function of what your endpoint is going to be. Okay? We'll continue on.